Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the URL shortener, the classic system design question that shows up in almost every FAANG and top-tier engineering interview. We will cover everything from functional requirements and non-functional requirements, through high-level system architecture and end-to-end user journey, all the way to low-level design, core algorithms like base62 encoding and Bloom filters, and the trade-offs you need to know. Whether you are preparing for a senior engineering interview or just want to understand how TinyURL and Bitly work at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the URL shortener, the classic system design question that shows up in almost every FAANG and top-tier engineering interview. We are going to design a service like TinyURL or Bitly that takes a long, ugly URL and produces a short, shareable link that redirects back to the original. We will cover the full picture. Functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core algorithms, low-level design, and the trade-offs you need to discuss in an interview. Whether you are preparing for a senior engineering interview or just want to understand how these systems work at scale, this one is for you. Let's get into it. Here is the core problem. The web is full of long URLs. A product page on an e-commerce site can be hundreds of characters. A tracking link from a marketing campaign can be even longer. These URLs are hard to share on social media, in SMS messages, in emails, or even in printed materials. A URL shortener solves this by mapping a long URL to a short token that is easy to remember, share, and track. But the design is tricky because billions of links might be created. Each click must redirect in milliseconds, and the system must never accidentally map two different long URLs to the same short code. Add to that the need for analytics, custom aliases, expiration, and abuse prevention, and you have a real system design challenge. Let's walk through the functional requirements. First, the system must be able to shorten a long URL and return a unique short URL. Second, it must redirect a user from the short URL back to the original long URL with minimal latency. Third, it should support custom aliases, so a user can request a memorable shortcode like bit.ly y/sale2026 instead of a random string. Fourth, it should provide analytics such as the number of clicks, geographic distribution, refers, and timestamps. Fifth, it should support link expiration or deletion so users can take down links. These 5 capabilities form the contract of a production URL shortener. Now the non-functional requirements. Redirect latency is the most critical path because every click goes through the shortener. It must be under 10 milliseconds at the 99th percentile, and ideally under 5. The system must be highly available because a broken redirect breaks the marketing campaign or the social media post. It must scale horizontally to handle millions of shortens and billions of redirects per day. The short codes must be durable and unique, so we cannot lose the mapping. The system must be read-heavy, since there are usually many more clicks than link creations. And finally, it should be cost-efficient because storing every click event for analytics can become expensive quickly. Here is the high-level system architecture. On the left, clients hit the API gateway for shorten and redirect requests. The gateway handles authentication, rate limiting, and routing. For shorten requests, the right path goes to an application service that generates a unique shortcode, checks for collisions using a Bloom filter, and writes the mapping to a persistent NoSQL database like DynamoDB or Cassandra. The mapping is also cached in Redis or Memcached for fast redirects. For redirect requests, the read path checks the cache first. If there is a cache miss, it falls back to the database, populates the cache, and returns the redirect. An analytics pipeline consumes click events from Kafka, enriches them, and writes them to a data warehouse for reporting. The entire system is fronted by a CDN for static assets and a load balancer for the API layer. The key metrics you should memorize cold. Redirect latency at P50, P95, and P99. Shorten latency. Cache hit rate for redirects, which should be very high, typically above 90%. Collision rate during code generation. total number of short URLs, and total number of redirects per day. Analytics ingestion lag and query latency for the dashboard. These metrics tell the interviewer that you understand this is a read-heavy, latency-sensitive service with a simple data model but massive scale. Let's trace the end-to-end user journey. A marketer on an e-commerce platform generates a long URL for a holiday sale page. She calls the shorten API and receives a 7-character short code. She tweets the short link. A user sees the tweet, clicks the link, and the browser sends a request to the shortener. The shortener looks up the short code in Redis, finds the original URL, and returns a 302 redirect. The browser follows the redirect and loads the sale page. Meanwhile, the shortener logs the click event to Kafka, which is later aggregated into a dashboard showing the marketer that her tweet drove 10,000 clicks from the United States and 2,000 from India. The core models and algorithms. The most common encoding scheme is base 62, which uses 62 characters, uppercase and lowercase letters plus digits. So a 7-character code gives 62 to the 7th power, roughly 3 trillion unique combinations. We can generate short codes using a centralized counter or a pre-generated key set. To avoid collisions without hitting the database every time, we use a Bloom filter in front of the code generation. The read path uses cache aside with a short TTL. For analytics, we aggregate click events into time series buckets. The key trade-off is between sequential counters, which are simple but can leak business metrics, and random codes, which are harder to guess but require collision handling. Now the low-level design deep dive. The database stores a simple mapping table, short_code as the primary key, long_URL, user_ID, created_at, expiration_at, and click_count. The short_code is a fixed-length string, typically 6 or 7 characters. Because the read pattern is short code to long URL, we can shard the table by short_code prefix. The Redis cache uses the short code as the key and stores the long URL plus metadata. The redirect handler returns a 302 permanent redirect to minimize SEO impact. For custom aliases, we maintain a separate table with a uniqueness constraint. For abuse prevention, we run the long URL through a blacklist and rate limit per user. The analytics pipeline batches writes to reduce database load and uses an asynchronous queue to avoid blocking the redirect path. Key takeaways for your interview. First, the URL shortener is a read-heavy, latency-sensitive key-value lookup problem, so emphasize cache and database choices. Second, base 62 encoding and collision handling are the core algorithms. Be ready to explain the trade-offs between counters and random keys. Third, redirects must be fast, so cache hit rate is critical and a 302 redirect is preferred. Fourth, analytics and abuse prevention must be asynchronous so they do not hurt redirect latency. Fifth, scalability comes from sharding by short code and using a CDN for static assets. If you can walk through this system with these 5 points, you will signal solid senior-level design thinking. That's it for the URL shortener. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the URL shortener. We covered the full picture from shorten and redirect flows, through base 62 encoding, collision handling, Bloom filters, and cache design, all the way to low-level database schema and analytics pipelines. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.